Okay, good morning. Welcome back to the lecture. Let's start now. First, there is a correction on this title here. This example we discussed yesterday was actually a 28-bit pipeline header instead of 22-bit. It's 28-bit here. So now we have finished the session of adders. Next session is multipliers. Well, a binary multiplier can be implemented in a number of ways. The first approach is a pencil and paper method. So consider we wanted to find the product of two binary numbers, A and X. We can write number A in this format as the summation of terms of 2 to the power k. So here the coefficient of AK is either 0 or 1. And then so we get this form of the product. So basically what we can do is to find the 2 to the power k times X. If AK is 1, if AK is 0, then this term is 0. So for each term, we have 2k times X. So basically, this is X times 2 to the power k is a shift of bits. It is shift of X bits to the left by k positions. The shift. And then we have a total of n terms if A has n bits. So basically this is a shift and add, That's a pencil and paper method, also called a serial and parallel method. Here, one operand is used in parallel. X is used in parallel. And A is used bitwise. So, and this requires n long adders, n adders. And it will produce a latency of n clock cycles. A second approach to implement a binary multiplier is named as the serial approach. In this approach, we also expand X into something like A. Then we have two summation signs, one inside the other. And with this, we only one full adder, only one bit full adder is required. But this takes a long latency. The latency is n squared cycles because we have a summation inside summation. The last one we will discuss is a parallel approach. And it's a very popular approach. To explain this, let me use the whiteboard. Let's consider the product of two numbers A and B, each has 4 bits. So this number A, the subscript here represents the bit position. This is MSB of A. This is LSB of A. And B we want to find a product. So A0 times B0, and we call it PI P00 here. I use this notation. PIJ equals to AI times BJ. I speed of A times B, J speed of B. So this is A. It's A1 times B0, so you call it P10. This is P20, P30. Then we have this A0 times B1. So this is P01. And here P11. P21, P31. Here, the A0 times B2, so P the 02, yeah, P12, P22, P32. And here, A0, P3, and P03. So this is a bitwise product, and it can be easily implemented by an AND gate. To input AND gate. Now we want the product is the sum of these columns. But if you just perform a summation here, then it just returns to the first approach. And this third approach here use a cell array. I mean the adder cell array of. Consider this. So this P00 can directly appear as the LSB of the final product. We call it P bracket 0. Now, I add a cell here for the second position here. So these two are added together. These two are added together to give out P1. So this is adder produce a sum output. This is sum output. It can be and there's another carry output. So carry output will be somewhere to the higher position. I will talk about carrier later. So that's the second column from the right. Then the third column, we should add these three together, and also the sum, and also the carry output of the previous column. We added this P20, P11 together, and the sum output is add with P02. This output, the sum output is P2 here, and there will be carry output. Let's consider carry input here. So the carrier of this adder, carry output of this adder, can be applied to any position, any adder here, any of adder in this column, because it just needs to propagate to a higher position. But here we propagated the carry output to a lower row, always to a lower row, for a reason that you will see very soon. And also this two adder cells will also produce carrier, but let's talk about the carrier later. Now here, the fourth column, this column here, we want to add this four partial product together, and also with the carrier output of previous column. And we go from first row, and first row and second row add together, and this adds with the third row, and adds with the fourth row, and also take care of the carrier output of the previous column. We do it like this. Then the sum output is the P3, the P3 of the final product. There will be carrier output. Talk about it later. And then on this fifth column, I put the adder cell here. This P31 add with P22, and the output further adds with P13. So that's the three elements, but we also need to care about the carrier output from previous row, previous column. And also there is a carrier here, carrier output, and this gives P4. The same way, move to this sixth row. P3 add with P32 add with P23. Then we need to handle the carrier. Lastly, P3C should add the carrier output of the previous one. Carrier output is P7. This may have a carry out. Okay, so that's the array structure. Now let's look at the type of adder. For the first row, each of this adder cell has 2 inputs only, so they can be half adder. As shown here, half adder. Then the adders here, they are full adders because they have, each of them has 3 inputs. So these are full adders. Full adder. Half adder. This one has only 2 inputs, half adder. Okay, so that's this array adder. Do you have any questions with the structure here? Okay, now let's see features here. So we see that the carry output does not go to the same row, goes to the next row. So we have this shift in different stages. And with this arrangement, the hardware is very efficient. We just have some array of individual adder cells. We have an n square adder cells, and some of them are half adder cells. Although most of them are full adder cells. And this is an efficient hardware implementation for binary multiplier. So are you okay with the implementation method here? If no problem, let me move forward to other multipliers. For a higher speed, the multiplier can be implemented using the concept of pipeline that we discussed in the section of adder. And here shows an implementation approach. So we consider the number A. Here we consider product of A and X. A, we decompose it into bits. So this is LSB. A7 is MSB. So it has a weight of 128. X is the other binary number. So this top row means the X shift, the bit of X shift towards left by 7 positions. So it's multiplied by 128. A7 is either 1 or 0. So that's the partial product. So other rows other partial products. So we have this x, 2x times a1, 4x times a2, and so on. So these are calculated simultaneously in order to improve speed. This parallel calculations. Then we should add these 8 rows together. And in the addition, we can add, we can do the addition in this manner. So we add 2 rows. We divide this into 4 groups of 2. So each group is added. Then we have another stage of addition and final stage of addition. So by doing this, we can use some registers here to install the intermediate output. And then we can also here registers store values. And also register at the input to store the partial products. So with this, we can implement this in a pipelined manner to increase the throughput of the multiplier. Is there any question regarding this? If no, let me move on. The next one is a, I would say it's a subset of multiplier. It's used to calculate so-called inner product. We want to compute the sum of products where the coefficients are known. It's like in FIR filter. You have input and you have a filter, FIR filter. You have a filter there, input, and this is a convolution process. Input is time variant, the content of input. The number input number is varies, you don't know. But the filter coefficients are known. Filter coefficients are clearly defined, fixed for a given filter. So, and say we wanted to calculate this inner product. This is an implementation of like FIR filter. We want to find the inner product of C and X. C is the coefficient, X is the input, Y is the output. The inner product or dot product. Mathematically, so we have the summation of Cn times Xn, where n in the bracket is the time index. We have, say, for a nth inner product, we have an nth term for X. So this is inner product, you know, this inner product. Well, C, the coefficient of C is known. X varies. And for this special product, this inner product, there are efficient hardware implementation. And we're going to discuss about this. Well, if we expand it, it's just C0 times X0 plus C1 times X1 plus Cn-1 times Xn-1. Each of, C and X, each of them is a binary number. A straightforward implementation is like this. You store the X in some register, C in some register. And this register is a long word. Each of this content is contains several bits. So X times C, X0 times C0. Then you store it maybe in a output register. Then you add this with the previous result. So this is a summation. This is accumulation function. Accumulation. This addition register and registers output. provides a delay, and the delayed version is added back to the current for input. So this equation is implemented by this hardware structure in a straightforward manner. But this is not efficient. You need a multiplier here, which is costly in terms of both number of gates and the latency. Now, an efficient way to implement the inner product is to use the distribute arithmetic. Now we consider X, or we represent X in terms of its bits. The subscript B represents the bits, individual bits, and here inside a bracket refers to the time index. So xn is represented bitwise. So xb, each bit of x is either 0 or 1. It's common binary representation. And C is coefficient of the filter or of the inner product. We don't expand it into bits. C just there. So the product Y can be represented as this: C times xn. This inner product, Cn. So we have for the nth order of inner product, time, we consider n time elements. Cn time, this is Cn, and this is xn, x value at time n. So here we have a so we can expand this product and redistributing the order of summation as follows. Because we do this redistribution of the order of summation, we get the name distribute arithmetic. Distribute. So here this equation is expanded here. So C0 for time index 0. And this is x0, x at the time zero's value, expand into this expanded binary format. These are x. The subscript refers to the bit position. The bracket refers to the time. So this is C0 times x0. But x0, x at the time 0, is expanded. Now this is C1 times x1. So on. So n terms, inner product. N's or inner product. Now we want to redistribute the order of summation. We want to group this 2 to power something as a term. So we wanted to let me just pen here. We group this, and this together. They will multiply with 2 to the power b minus 1. So here. And same for this 2 to the power b minus 2. And we have this this one, this coefficients, not coefficients, this term, this. Okay, is C0 times b minus 2 of x at the time 0, and at time 1, and at the time n minus 1, all the way to this 2 to the power 0 term. Here we have all the time information here. 0 times 0, c at time 0 times x at the time 0, but be 0 and so on. Now, in compact form, this result can be written in this way. We have a total of n terms, and each term time is a something times 2 to the power b, small b. B is b ranges from 0 to b minus 1. Let me go. Here you see. Say if we look at this, this we have b terms here. B terms. Inside each term, it's a function of c and x. Inside each term is a function of c and x. It's a summation of cn and x times a summation of this product terms. Summation of cn times x sub b of n. And we call this product cn times xb as a function of cn and xbn. Now with this, for each of this term, f term, it can be realized by a lookup table. C is known, filter coefficients. C's value at each time is known. And we treat x as the input. In this way, so we can well, actually, we implement this inner product with this hardware structure. Let's take a look at the input side. We have x. It's arranged in this way. For time 0, this first row is for time 0. We have a bit from xb all the way to x0. The rightmost is the least significant bit. Then this is x value at time 1, bitwise, arranged in a bitwise manner. And this is x value at n minus 1, arranged bitwise. Now, for these significant bits of x value at different time, they are input to a lookup table. This lookup table checks the checks this value, checks the C and X sub B's value. Say, let's consider n is 0, n is 0, time is 0. Well, later, next slide, we have an example, and you get it more clear. So this is the least significant bit. The product with C can be obtained through the use of lookup table. And then we move to the next bit, the bit 1, bit 1. So product with C is found from the lookup table. Then it needs to add with the previous result because previous result is from the LSB. So the value should be divided by 2, or the bits should be shifted towards the right by 1 position. Then add with this. So each time you divide the result by 2 and add with the higher bit product. Maybe from this is too abstract, but now through this example, things will be clear. So let's consider third order inner product. Just 3 elements for C and N. 3 times. So N this is inner product. And the coefficients has this value. C0 is 2, C1 is 3, and C at time 2 is 1. The coefficients, we don't decompose it into bits. C is just here decimal numbers at a different time. 3 C, I mean, C has value at 3 times. Okay. Now, here the let me see, X so we have so here we construct a choose table, lookup table. Say this lookup table is to find the list. Okay, find these terms. Yeah. The C value are unknown. So C0, C1, C2 are known. And the X is varying. Let's assume X is a 3-bit number. So let's check here. Say X value at time 0, it has a value of 0, 0, 1. binary is 1 in decimal. X1 is 3, binary is 0, 1, 1. And X2 is 7, 1, 1, 1. So at the time 0, let me see. This is step and not time. Time 0 is here. Time 0 is here. Time 0, we get a 0, 0, 1. 0, 0, 1. And the first row is the significant bit, 0, 0, 1. And X1 is 0, 1, 1. 7, X2, 1, 1, 1. Now for step 0, the first step here, we calculate the coefficients for the 2 to the power 0. 2 to the power 0, this term. So we have C0 times, let me write it here. Here on the whiteboard. We have this C1 times okay, the first step is to calculate this. And C0, what is C0's value? C0's value is 2. C1 is 3. C2 is 1. 2, 3, 1, yeah. And this can be formed as X0 X at the time 0, the least significant bit is 1. This is 0. X then this X at time 1. X time 1, the least significant bit 1. This is 1. And then X at time 2, least significant bit. This is the total 1. Okay, it's simply 2 times 1 plus 3 times 1 plus 1 times 1. Here it is 2 plus 3 plus 1 is 6. It's 6, but this 6 can be formed from a truth table. From this lookup table. Here we can calculate these things, all the possibilities of X's value. So if for this picture, at time 2, time 2 X is this position is 1, 1, 1, we calculate it to be 6. For S is 6. Then we move to 6. This is formed from this lookup table. Here. Then we move to the power 1 this term. So it's C0 times this is X0. It should be X1. 1 corresponds to the fifth position, subscript is the fifth position. And this time index should be the same. Okay, C here is here 2. C is C's value are 2, 3, 1 there. Now X1's value. X the first bit bit 1. Times so that's the center position of the 0, 1, 1, 0, 1, 1. So 0 times 2, 1 times 3, plus 1 times 1. So it's 3 plus 1, 4. Okay, we also check from the lookup table 0, 1. Is 1, 1, 0 to be this time 2 is corresponds to the leftmost column. This is 1, 1, 0. 1, 1, 0. This is to be calculated. That is 4. Lastly, the MSB for the C, for the X. Subscript is 2, big 2. Here C's value are 2, 3, 1. Now let's check MSB of X times 0, 1, and 2. MSB mostly 0, 0, 1. 0, 0, 1. But from that table is written, it's starting from the MSB, so it's 1, 0, 0. 1, 0, 0. We calculate whether it's 1. Let's check whether it is 1. The 0 times 2, 0 times plus 0 times 3 plus 1 times 1 is 1. Okay, now we perform the sum of these 3 terms. So this is 6 is the ASB. So we have this 6 plus this 4. It's not 4, but it is to the power 1 plus this 1 is to the power 4, 1 times 4. The result is 6 plus 8 plus 4. It's 18. And you can make a check. This input that you calculate by hand is very simple. It's just C is equal. C is 2, 3, 1, 2, 3, 1, and X is 1, 3, 7. Inner product, this product. Inner product C and X is 2 times 1 plus 3 times 3 plus 1 times 7. What's the value? It's 2 plus 9 plus 7, it's 18. That's consistent. You see this this is different from this. I mean, intermediate scale are different. This is straightforward calculation. It requires the multiplication of these binary numbers. It's not efficient in terms of hardware and also in terms of delay. But if we can rearrange it, redistribute the order of summation, we get this structure. So this first here is for LSP for all the for X value at all the time. And we check from a lookup table. Lookup table is easy to construct. Lookup table here, you see F is just Cn times XP's value. Very simple. It's just Cn times it's just this XP2 times this XP2 is a 0 times C1. It's a C0 is 2. So 2 here, 3 here, 1 here. So C's value 2, 3, 1. 2 at the time 0 at time 0 and time 1 time 2. C's value 2, 3, 1. And this multiply the this corresponding value of XB. So this is Cn times X sub B of n. Then sum for all the time. So it's 2, 3, 1 times just this these values. We for 3 order inner product. We have this a total of 2 to the power 3, 8 combinations. 2, 3, 1 times 0, 0, 0, or 0, and it's 1, 0, 0, 0, 1, 0, so on. This can be pre-calculated and stored in the registers of a lookup table, and it can be calculated very efficiently. So this implementation for inner product is extremely efficient in terms of hardware and delay. All right, let's take a break. 5 minutes. Okay, let's continue. So questions on such kind of distributed arithmetic appeared several times in the past papers, so it's very important. In order to appreciate the benefit of this implementation, I suggest you to go through this example by yourself, and not just read it. You get a number of C and N's value. You write it down by yourself once. Go through it by yourself, and things will be clear. Actually, it's not complex at all. And you construct this choose table, this lookup table by yourself, work out the process. Now, for the distributed arithmetic, if the number of coefficients n is too large, and a single lookup table may not able to implement it because the number of inputs to a lookup table is n. Say if n is 8, then lookup table requires 2 to the power 8. This number of inputs, so it could not be implemented by common lookup tables. In that case, we can use partial tables. We can split those in those lookup table into parts. This one represent lookup table. Then add the results. So this is referred to as a table partitioning. Say for a four order lookup table, 4 order inner product, you require 16 inputs for the lookup table. 16 input. Say if your hardware cannot support 16 input, you cannot only support 8 input lookup table, then you can split it into 2 lookup tables. That's the idea. And with this splitting pipeline concept can be implemented as well to improve the speed. One thing I would like to point out here is that in this calculation, we multiply the bit 2 with 2, multiply bit 2, the third bit with 4. We implement with multiplication, but in the hardware implementation, we perform a division by 2 for the lower positions. For each time, we divide it by 2 and then add it to a new value. And this is the division is more hardware efficient. Then or you can do another way is you don't do this division. You put the multiplication by 2 here, but it's also okay. The same thing. You don't do this division. You move this. You add multiplication by 2 here, and you just get another one. Oh no. If multiplication by 2 there is not I think it cannot do that. It better stick to this one. You divide the lower bit by 2 and accumulate. Each time you increment a bit, you divide all value by 2. Just stick to this structure. Another way to improve the distributed arithmetic architecture is to use word parallel approach. So in our basic DA architecture for links and sum of product, we accept 1 bit for each of the n words. We accept 1 bit. 1 bit in each of this product. 1 bit. Actually, we can combine this two into one. We can do 2 bits at a time. So we can do something C0 times x1, x4, and then this x1, x2 or something combined 2 bits at that. So this is 2 bits. If we make this 2 bits, then so 2 bits per word, 7. The computational speed can be doubled. But lookup table becomes more complex. So that's another way to further improve the performance of the DA architecture. Okay, now here let's move to the final section of this important part. The final section is a simple processor. So in this session, we will exercise our design skills by designing a simple programmable processor. So we will design a simple programmable digital signal processor, DSP. And this DSP is not pipelined, and it should not be considered as an exercise in high performance CPU design. However, this design allows us to go through the basic elements in a microprocessor. So this processor is a simple computer with separate instruction memory and data memory. And this architecture is called Harvard architecture. And this computer architecture is called Harvard architecture, separate instruction memory and data memory. Our DSP, our processor is here. And this processor uses 16 bit words for both instruction and data. The instruction, each instruction is a 16-bit long word. And for the DSP, we're going to implement the instruction set is given here. It has just simple few instructions. First is the add and subtraction. It performs the addition of register 0 and register 1. And the result will be stored in register 0. Subtraction is the same. Subtract register 1's content from register 0's content and store result on register 0. The second type of command is load and store. Is to load the data memory with address here, with certain address, to load a lot and store and load a lot of value to the source, to the destination register. And register's position is address is given here. Store is to store the data contained in the source register into the data memory with this address. And jump is jumps to a specific program counter. This is an offset of the program counter. Is to jump from the instruction memory. Another jump command, it should be jump 0. Jump, conditional jump. If register 0, the content of register 0 is 0, then it will jump. Otherwise not to jump. And no operation. Sometimes we need this one. So lastly, simple instruction set. But although simple, this is a complete microprocessor. Okay. This figure shows the microarchitecture of our processor. It consists of 3 major units. The register file. We need some registers to store intermediate values. The ALU, arithmetic logic unit, which performs computation, and the execution unit, which provides the control. The register file together with the ALU, these 2 block units, together form the data path that we discussed today in this part. The execution unit is responsible for fetching instruction and decoding instruction, as well as guiding the data path through the execution of the instruction. We fetch instruction, decode it, and execute it. And the encoding of the operation codes are shown in the right. We have this 7 commands, 7 operation commands, add, subtraction, load, store. They're given here. They are coded here. Add has a code 0, subtraction code 1, so on. Now, let's design the 3 major units in the processor. We start with the ALU, which is the simplest one. ALU here. ALU. Here we have a module. We define a module ALU. Its ports are given here. It has input clock and input F code. F code is the operation code. This operation code here, we have 7 operation F code. F code is a binary number here. It has the so the operation code has the bit length of 3. This F length, operation code length 3. This is a programmable processor. So we have this parameter here. We define this parameter, the length of operation code. And the input data, operand. We have 2 operands, op 0 and op 1. And this input, each operand is n bit wide. N is a parameter. Here is programmable, but default value is 16. Output value result. Output is this output port result is also an n bit wide. And another output is to indicate overflow, output overflow. Okay. So this output result and overflow are register type of port. Now here is the content of this ALU. Execute the following block whenever there is activity, a change in the F code. First, in this block, we define the result, initialize the result as unknown. The result is 16-bit unknown. Overflow is 1-bit, it's also unknown. Defined as unknown initially. And now look at the case of the operation code. Although we have 7 operations, but this data path is so only the add and subtraction is responsible by this ALU. Other load store does not need the ALU, does not need to go through ALU, jump other things. So only add and subtraction is involved in ALU. But here we implement a few more operations. So operation code, if it is 0, then it is addition, defined parameter. If it is 1, is subtraction. So if it is operation code is a plus, then we perform the addition of this operand. Result given in the sum is given in result, and the carry out is given in the overflow output. This concatenate outputs. Subtraction similar, just subtraction instead of addition. Here, besides the plus and minus, we also implement some other functions like +1, which is to increment the up 0 by 1. -1, this is a decrement the up 0 by 1. And negation is to negate the value of up 0 and produce the result, output at the result. That's the ALU. Let's talk one more unit today. It's a register file. We define module, register file. From here to here, a module, not long. And let's look at the port, clock input. So here in this, we have in this register file, we have 4 registers. Number of registers is 4, which is programmable, and the word length is 16. As I said, it's 16-bit processor. Input port here, we have this register A's address and register B's address. So it has this address has a length of 4, defined by n register here. The output port register A's value and register B's value, data value. Say it can be this op 0 and op 1. Input, so register A read write, register B read write. If this input signal is 1, then we will write into the register, write some data into the register. If this is 0, then it's a read operation, no write. Now input write, so register A writes is content to write into register A. And register B writes content to write into register B. And then we have a register file. We have 4 registers from 0 to 3. And each register contains 16 bit, is 16-bit wide. And that's the register file. Okay, so that's the basic structure. So the operation is simple. To read the register value, we just assign. So say if this register A value is low, then we read it. So we just assign the register file, so with address given here, this contents value into the output port register A value, and register here B's address and the content here, pass that into register B's output port. To write, it is a synchronous circuit. We have this always block at the rising edge of a clock. If register A rewrite this signal is high, then we're going to write it. So we assign the input port read A write, this input port data. We assign this input port data into register file position given here at the register A's address. A second row here is to write the register B's value into register B's content. Okay, so the register file here is just a block of memory that can be read and written. And in this design, we use 2 ports. So this, our register file supports 2 simultaneous reads or write. We have 2 ports, register A and register B. You can simultaneously read or write these 2 registers. Okay, so that's the register file. Any questions so far? So we'll talk about these 2 simple units. The execution unit is a little bit complex. I'll talk about it next time. But before finishing, I would like to talk about homework. The homework 3, some final state machine problem. 2 questions here. Let me briefly talk about this. So this is taken from our previous part of lecture notes. It's a mini final state machine. For question 1, is similar to this one. So this is a final state machine to recognize the sequence of 1, 1, 0, 1. let me go through how to construct this. So first, we have an initial state. Let's call it state A. Initialized when the signal comes in, the machine is in state A. Now we have input X. If input X is 0, it doesn't match with the first bit. It will be stay in the machine will stay in state A. Now, if input is 1, X input is 1, and matched with the first bit of this pattern, we're going to recognize that. Then it goes to next state, B. And if next bit is also 1, it matches with this one, I'll go to state C. If next one is 0, 1, 1, 0 goes to state D. Almost there. And if state if the next bit is 1, okay, next bit is 1. 1, 1, 0, 1 is matched. We give an output of 1. Output here is not stated. The all output are 0, assuming output are 0. Otherwise, if it's 1, I specify. The output is 1 here. Okay, but when output is 1, what's next state? It's 1, 1, 0. If output is 1, it actually matches with this first what? First bit, state B goes back to state B. So that's the main loop. So 1, 1, 0, 1 goes back to state B. And we also need to deal with other branches in each state. Here for state 0, 1, both input possibilities are considered. That's okay. For state B, if it is 1, we already consider. If the input is 0, then either the input is 0, it won't match. 1, 0, it won't match this pattern. We need to go back. If input is 0, we'll go back to state A. Right. Then here, state C is 1, 1. 0 is considered. If input is 1, which state should it go? I go back to C because 1, 1 still match this pattern. In 1. For state D, input 1 is considered. If input is 0, where should it go? What is the next state? Go back to A. Very good. So that's the pattern recognizer. The homework question 1 is similar to this one. Now, then this question is more complex. I show you partial solution. Okay. So this is a vending machine. Coins are insert into a slot and rolls down, and the coins will be sensed by 3 light sensor X, Y, and Z that position at different positions. If a $1 coin rolls down, it will only block this light sensor. Sensor Z. So sensor Z will produce a signal high, say. X and Y will be maintain 0. So it will so sensor Z will go high for a certain period when this $1 coin rolls through it. And then when this $1 passing through Z after 1 clock cycle, we should give out a output signal, a D1, to indicate that $1 is detected. And if $2 rolls in, it will block both Z and Y. But Z is at a lower position, it will be blocked for a longer time. So Z will be high for a longer time than Y sensor. And if $5 rolls in, it will block Z for a time longer than Y, and Y is longer than X because of the coin is round. And after this falling edge of Z, respectively, so the D2 or D5 output should be produced for 1 clock cycle. So that's the requirement. The key in this question is to find the final state machine. Now let's say we have a state called phase 0, initial state. When we start the machine in this state. Now if the my sensors are 0, 0, 0, 0, let us consider the Z state, that means 0. It will remain in this state, right? X and Y, this X, Y, Z, X, Y, Z sensor. X and Y, I don't care. I look at Z only. You see 0, then no change of state. Now, if Z changes to 1, X, Y, I don't care. Only check it. Z input is 1 and go to next state. So stay here, 0, 0, 1. This state, I call it state 1. Okay, if this Y and Z remains at 0 and 1, 0 and 1. 0, 1, this is X, Y, Z, and X is don't care. 0 and 1, it will remain in state as 1. Then when Z goes down to 0, I'm going to produce D1. So if the Z goes to 0, I go to a state called S4, and if goes down to F4, it will soon produce make an output to 1. This is a Moore machine. It stays here. If it's not stated, output will be 0. Here D1 is 1. When this C input goes to 0. And then this will return back to the initial state. No matter what the input is, give out a pulse of 1 clock here. So that's the detection of coin Z. And there are some. So S1, if something here, say if it is here, C1 here, C1 7 here, C1, C1, but now Y goes too high. If Y goes too high, Y goes too high, then goes to next state. And so on. The rest is for yourself to figure out. All right, let's stop it here. Any questions? If no, thank you for coming. I'll see you next week.